In this session, we are going to learn about energy. Now, let us ask one very important question, and the key question is how energy is stored and transferred. After the session, you should know examples of how energy are stored and the way in which energy is stores can change in energy store can take place. Next, you will learn how to calculate work, how to calculate kinetic energy, how to calculate gravitational potential energy, and at the end, elastic potential energy. So let us begin. First question is, why do we need energy? So the answer to this question is very simple, and that is to make an objects move, make objects move, and yes, of course, keep devices such as mobile phone working. There are so many appliances we are surrounded with that works based upon this energy, right? So now the ability to access energy at the flick of a switch makes life easier, as we all know. Right now I'm also using energy to reach to you. My sound is reaching to you. I am able to speak to you. You are able to hear me. This is all because of certain exchange of energy taking place, right? So most of the energy you use is obtained by burning fuels such as coal, oil, gas. And cars, buses, planes and ships all use fuels as chemical energy stores. We'll talk about this. They carry their own fuel. Now, electric trains use energy transferred from fuel in power stations, where the electricity transfers energy from the power station to the train, right? Okay, you see here. Now, here is this. With the help of this flow chart, you can understand in what different ways energies are stored and transferred. So I have made a list of it. So you can see here, energies are stored as kinetic energy store, gravitational potential energy store, elastic potential energy store, and chemical energy store, right? Thermal energy store. How they are transferred, we'll talk about that. It is transferred as heat. What happens when we rub the palm? What happens? With this sort of, we do some kind of work to overcome the friction, and that sort of get transferred as heat. That work done is transferred as heat. So this is sort of stuff you need to learn in this section. So heat transfer is done in another way as wave, light wave, sound wave. There are various waves as an electric current. And when a force moves an object, suppose I am lifting this pen up. So in the process of doing so, what I did, I had to do some kind of work, and there is a transfer of energy taking place. When I do some work, there is a transfer of energy taking place. We'll talk about that shortly. Now, let us talk about different energy stores. So first is kinetic energy. It describes the energy of an object due to, mind it, an object or a system of objects. This is important. When it is in motion, right? It is in motion. So like here you see this car is moving, car has got some sort of kinetic energy store in it. Now, let us try to understand what is gravitational potential energy. First of all, I want you to remind yourself of this potential energy. When you say potential energy, it is related to position. It is related to position. Any change in position will change the potential energy. In this session, we are going to learn two types of potential energy: gravitational potential energy and elastic potential energy, right? So what is it? Now let us understand. It describes the energy stored in an object because of its position, such as an object above the ground. You see here, right? You see here, this ball is above the ground, and this is here, right? This is ground, and this h height above the ground, and that is why it has got potential, gravitational potential energy stored in it. Now let us talk about elastic potential energy. This must remind you of something that regains, shape and size, something that related to elasticity, elasticity. So sort of springy object, right? When you stretch it or squash it, what is happening? Energy is stored in that. So here you see, you are squashing it. If you stretch it, then also there would be energy stored in it. Elastic potential energy, we are going to learn very soon. We'll calculate how to calculate this. We'll learn it. Okay. Now, chemical energy store. We all know that food we consume, and we have got our energy so that we can do whatever we do in our daily life. So that sort of energy that is stored and related in the food, associated with the food, is chemical energy. And chemicals found in the battery is also sort of chemical energy, right? Fuel also is a sort of chemical energy. This is what you have. You see here the battery. This region, in this region you have this one, there is some chemicals in this region, right? Electrolyte. This electrolyte, this cathode, and this anode. This positive terminal, this negative terminal. This negative, this positive of the battery. This is the outer side, you can look at here. So chemical energy store. Next is thermal energy store. It describes the energy stored in an object due to its temperature, right? You see here what is happening. This is a stove, and you see here the flame. This pan is getting heated. You touch it and you feel that heat, right? So due to temperature you have got thermal energy. All right. Now let us talk about how energy stores can be changed from one to another. This is very interesting, and you will understand this very easily. Changes in energy stores in electric kettle. When an electric kettle is used to boil the water, the current in the kettle's heating element transfers energy toward the thermal energy store of the water and the kettle, right? So try to understand the transition from one energy store to the another energy store. We have some more examples. Look at this. Changes in the energy store of a torch lamp. What is happening here? This is happening. With the flow chart, you can understand how energy is getting transferred from one energy store to another. So what was there? Battery was there in the torch lamp. So chemical energy stored in the battery is getting transferred in the electric current, in terms of electric current in the wires. Next is it is the energy transferred to the surrounding, and it is getting transferred in two ways: increase in the thermal energy store and light wave, right? Light wave. Okay. Now another example. This is very interesting. Changes in energy store of a falling ball. If I drop a ball hits the ground, and there is some transfer of energy taking place. Changes in energy stores taking place. So look at this. All right. Now with the flow chart, you can understand kind of changes in the stores of energy. You can see here above the ground. If you remember, we had talked about this. Above the ground, if you are keeping an object, it has got gravitational potential energy stored in it. Now as it comes down, the gravitational potential energy is decreasing, right? So when it is decreasing, what is happening? It gains some speed. It gains some speed. So gravitational potential energy store is changing in kinetic energy store, and further it is transferred to the surrounding, again in two manners, right? Sound wave and increase in thermal energy store. So that is interesting. Now let us calculate what is work. This is very interesting. This is very interesting. When an object is moved by a force, work is done on an object by the force. Force transfers energy to the object. The amount of energy transferred to the object is equal to the work done on it. So this is the equation that you need to keep in mind. That's very simple. If I am supposed to move this, so what I'm doing, I'm transferring my muscle energy, right, into the kinetic energy of the object. I'm transferring energy to this object. So work done can be considered as, it is equal to what? The energy transferred. Amount of work done equals amount of energy transferred. So this is the basic stuff. Now how do we calculate it? That is important. Work done by a force depends on its mass. Work done by a force depends on size of the force and the distance moved along the line of force. I want you to understand this. Suppose there is a box kept here and I have applied force, pushing force, and this has moved from this distance, this location, to this location. So the distance moved is, let's say we call it d. Okay, this is distance moved. You need to understand this very simple thing, that the displacement, this distance, basically distance moved by the object, must be along the direction of applied force. So force is applied in this direction, so this is the line of action of force, we can say, and this must be same as the distance covered by the body. This is what we need to understand. Likewise, suppose you can think of it, suppose coolie is sort of keeping a luggage on his head and moving in this direction, Can we say that work has has been done by this coolie? No, because he is applying his force in this direction. He is applying his force in this direction to keep the luggage intact, and he is moving in this direction. So force applied is in this direction, and motion is, and the distance that he has covered is perpendicular. It is not along the direction of applied force. So that is why work done in this scenario will be 0. So this you need to keep in mind. This is very simple. So that was an example where you can understand why this is important. Force applied and distance moved along the line of force. Next is very important. You need to understand this, because if you understand this, then only you will be able to answer questions which I have taken in the assessment session. So here we need to understand how friction works. Work done to overcome friction is mainly transferred to the thermal energy stores by heating. As I have told you, rubbing your hands, right? Look at this. If you rub your hands together vigorously, they become warm. They become warm is what? The energy transferred is to the thermal energy stored. Thermal energy stores, right? Your muscles do work to overcome the friction between your hands, right? This we need to understand. The work you do is transferred as energy that warms your hands. How to calculate the changes in gravitational potential energy stores? This is quite important. I want you to notice this thing carefully. Two situations I have taken. One is when object is moved upwards, like I am taking it upwards. What is happening? Gravitational potential energy store is increasing, right? It is increasing. And this increase is equal to the work done. The work I have done to lift this up. Now focus on this. This object is moving upward, right? Upward. I am also applying force upwards against the gravitational force. So that work done is stored as gravitational potential energy. Is that clear? So this we need to keep in mind. Now, when an object moves down, what happens? This decreases the gravitational potential energy, right? Gravitational potential energy. And of course, now what has been done? Look at this. If it is coming down, we know that gravitational force is acting downward. So the force that is doing work here is gravitational force. When object comes down, this work done is by the gravitational force. So now let us calculate the change in gravitational potential energy store. So this thing is very important. When you say that change in gravitational potential energy store, it is equal to weight. Of course we are doing calculating it in terms of work done, right? So it is weight into the height or the distance moved, right? Work done equals what? Force into distance. Force into distance. So weight, we all know that weight equals mass into gravitational field strength, and the change of height, suppose, is h. So this is the change in gravitational potential energy. Gravitational potential energy. This is important, as mass is measured in kilogram, gravitational field strength is measured in Newton per kg, change of height is measured in meters. This is important. These units must be kept in mind, right? So this way. And one very important thing, you all know that joule, 1 joule, which is the SI unit of work, is equal to 1 Newton meter. 1 Newton meter. So this will help you. Okay, now let us move further. Let us talk about the kinetic energy store. How to calculate that? The energy stored in an object when it is in motion depends upon two things: mass of the object and the speed of the object. So the kinetic energy is given as this. This is measured in joules, mass in kilogram, and speed in meter per second. So kinetic energy, equation of kinetic energy is this. Equation of kinetic energy. Half multiplied by mass multiplied by speed square. And you know the units now. Very good. Now let us move further. And one more thing before I proceed, let me come back to the same slide. If you want to stop a moving car or something, you need to do work, you need to apply force, that braking force, right, that will stop the moving car or whatever object you have taken. So that work done equals the change in kinetic energy. So suppose there is a question in this, we'll talk about that. Suppose it has got some energy, kinetic energy, and when it stops, kinetic energy stored becomes 0. So work done is also calculated as that change in kinetic energy. So with the help of this basic idea, you can solve that problem, numerical problem. Now let us talk about elastic potential energy of spring. You must have observed this thing. And when you stretch a spring, what happens? You need to do work against its elastic force. Mind it, this elastic force, this is interesting, this is very important. Elastic force. So elastic force and extension are directly proportional. This is elastic force and this is extension in the spring. Extension in the spring. Suppose you stretch it beyond certain limit, beyond its elastic limit, then what will happen? It won't come back to its original shape, original size. This is called Hooke's law. At this moment this is not that important, but one thing is very essential here. F is K into E. This elastic force is K, this is called spring constant, and E is extension in the spring. So energy, elastic potential energy stored in a spring is calculated as the work done. Work you do in stretching is stored as elastic potential energy. So it depends upon spring constant and extension. Now, here goes with this. The formula of elastic potential energy is half multiplied by spring constant into extension square. So this is in meters. Extension is measured in meters. SI unit is this. Spring constant, Newton per meter, and this is in joules. Now, check your learning. So the first question that comes is, describe the changes to the energy stores that takes place when a ball falls in the air. Try to understand this. It is falling down. What kind of energy store is changing? Right now, suppose it is at rest, like this. It is at rest, not moving. It has no speed, no kinetic energy. So it has only gravitational potential energy. Gravitational potential energy. As it comes down, although you don't have to answer this in this manner, you need to simply answer this, that change in energy store is what? Gravitational to kinetic, only this thing. So, but just to understand, this is important. Here at this point, there is no speed, no kinetic energy. Only gravitational energy is there. As it comes down, it hits the ground with some velocity. So it has got kinetic energy here. It has got kinetic energy here. Now, next question. I want you to calculate this. Do it. When a cyclist applies brakes, his kinetic energy store reduces from 1400 joule to 0 in a distance of 7 meters. Calculate the braking force. This is important. So force, as you're saying here, see, it is very simple. Actually, work equals force multiplied by distance, right? So force multiplied by distance. If you rearrange this, this work is done at the cost of kinetic energy. So kinetic energy is becoming 0, right? So what is happening? This work done equals, so work done will be 1400 joules. That is what is happening. Very good. So change in kinetic energy equals work done. So distance will be equal to what? Distance done. We have to calculate what? We have to calculate force. So what's the answer? Can you calculate? Work by distance, right? Work by distance. Yes, you did it right. So this goes. What's the answer? 14,000 divided by 7. It comes as 2,000 Newton. What's the SI unit of force? Newton. Always keep this thing in mind. SI units, if you miss out, you will lose marks, right? So be careful on that. So this braking force is equal to 2000 Newton, right? Okay, it was only 7, right? So this divided by 7, so only 200 Newton will be the braking force. There is another question. Calculate the kinetic energy store of a football of mass 0.44 kg moving with speed 20 meter per second. So what's the formula for this? Half mv square. M is mass and v is speed. So half into 0.44 into v is 20 square. Now what's the answer? 400 into 0.44 divided by 2. So it goes in this manner. 44 into 4 divided by 2, and it is 88 joules. And how do we get Newton from here? Now let us do another question. Calculate the work done by a jogger running up a slope of height 10 meter The mass of the jogger is 52 kg. Gravitational field strength is 9.8 Newton per kg. Work done. So I want you to understand this very simple thing, that even though the path that the jogger followed is this, right? It is moving up. The change in its energy store is gravitational potential energy. Are you getting it? So we don't have to talk about this distance. We need to talk about this distance, right? This distance, this height. We have nothing to do with this path. It might be, stairs or whatever, multiple steps like this. Ultimate thing that we need to keep in mind is the height, the change in height. So ultimately, this work done is going to be mass into gravitational field strength into height. Mass is 52 kg. Gravitational field strength is 9.8 and height is 10. 5096 joules. 5096. So you have understood what we need to basically notice here. Here we need to talk about the height, change in height. Not the this path is not important. This path is not important. So gravitational potential energy store is changing. So how do we calculate this? Gravitational potential energy store is calculated as mass, gravitational field strength into change in the height. So that is why we got this as the final answer for work done. Okay, now this is very important question. Suggest a possible reason why the actual amount of work done is likely to be higher than the calculated value. There is some sort of resistance, right? Friction must be there. So the jogger has to do more work than this. He needs to transfer more energy to reach this, because some part of his energy that he is carrying is getting transferred to the surrounding, to to overcome the friction. Need to do more work to transfer some energy to overcome friction. Is that clear? Calculate the mass of a car moving with speed 30 meters per second, and the kinetic energy store is 360,000 joule. So kinetic energy store, we have this value, kinetic energy equals half multiplied by mass multiplied by speed square, right? So what do we have? We have 360,000 joules of kinetic energy, that is equal to half multiplied by mass, and this multiplied by 30 square, right? So what's the answer for this? So it goes like this: mass equals 2 multiplied by 360,000 divided by 900. Square of 30 is 900. So what's the final answer? 400. So it is 800, right? 800 what? What is the unit for this? Kilograms. So this is the answer. A mobility aid to assist walking uses a steel spring to store energy when the walker's foot goes down, and it returns energy as the foot is lifted. The spring has a spring constant 250 Newton per meter. Calculate the elastic potential energy stored in the spring when its extension is 0.21 meter. Can you calculate? So elastic potential energy, can you recall the formula? Elastic potential energy equals what? Half K to E square. Spring constant into square of the extension, right? Half into 250 into 0.21 square. So what's the answer? 125 multiplied by 441 divided by, so this is your final answer. So 5.5. So even this can also do, right? Approximately this can also work, right? Although it would be better if you put all the digits after decimals. There's energy everywhere. Where you find energy, the SI unit is joule, right? So there's the joule. All right, I hope you all have enjoyed the session.